Thank you for the introduction. So I have no conflicts of interest to disclose. So in my presentation, I will try to walk you all the way from a very simple ADC measurement to a high-dimensional diffusion MRI experiment. So we'll start with ADC, then go to DTI, then Hardy, then multi-shell, and then higher dimensional diffusion MRI involving multiple echo times and multiple tensor shapes. So at each step, I will try to explain to you what these changes bring to the table, so what kind of new information they add. And I will also try to figure out some guidelines for designing your acquisition. So which p-values do we need at each step of these, and which gradient orientations. And then finally, if time permits, I will also give some general acquisition recommendations and guidelines. So let's start with some background first. So let's quickly review the pulse gradient spin echo sequence, because this is like the main working horse of diffusion MRI. So if we remove the gradient pair, the pulsed gradients from this sequence, what we have is a spin echo sequence which generates a T2 weighted image contrast. And if we then add a diffusion gradient pair, so one dephasing gradient before the 180 refocusing pulse and one rephasing afterwards, we can synthesize the acquisition for diffusion weight. We can make it diffusion weighted. So the first gradient, it will cause a dephasing, a spatially dependent dephasing of the signal. If then there's no movement of the water molecules, the second rephasing gradient will cause perfect rephasing. And then we'll have a strong echo at the echo time. But if there is, if the water molecules are moving, the rephasing will not be perfect, and we end up with a reduced signal. So that's why our diffusion-weighted signal typically looks much lower in intensity. So the amount of dephasing and the position dependence of this dephasing is encoded in the Q vector. So if we want to know the direction of the diffusion encoding, we have to look at the direction of this vector. And if we want to know how strongly the position-dependent phase shift is, we have to look at its magnitude. And typically in a diffusion-weighted experiment, we acquire a series of images, and each image has then its own characteristic Q vector. Together, these vectors make up the Q space, so that's why a diffusion MRI experiment is typically referred to as sampling the Q space. So what are the B-values then? So in order to determine the diffusion weighting strength or B-value of the sequence, we have to also take into account, of course, the time between the two diffusion gradients, because that's the time that the molecules are allowed to move. So what do we really have to remember about this? So this is a simplified view of diffusion MRI. So we always collect a series of diffusion-weighted images. Each of these diffusion-weighted images is characterized by a 3D vector, which has a magnitude, and this magnitude is proportional to the diffusion weighting strength, or the B-value. And with this, we can sample the radial domain of the Q space. And then it also has an orientation, which tells us the orientation in which our diffusion weighted sequence is made sensitive to diffusion. So this is covering the angular domain of Q space. And the more diffusion we have along the diffusion weighting information, the less signal we end up with in the corresponding diffusion weighted image. And also, if we increase the diffusion weighting, we will get more diffusion-induced signal loss. So if we are at the center of this Q space, we have no diffusion weighting. We have a high signal-to-noise ratio, but then if we go outside and outwards and increase the diffusion weighting, our signal will progressively become lower. And the recurring question that I will try to answer in this presentation is, at each step of the plot that I showed you in the beginning, what are the optimal gradient directions and p-values? So the first question we have to answer is, what are desirable qualities for an optimal acquisition scheme? And I think the easiest approach is to optimize your acquisition settings to minimize the variance of your parameter estimates that you want out of your MRI experiment. And one tool that we can use for this is the Kramer-Rao inequality, which will provide a lower bound for the covariance matrix of any unbiased estimator of a parameter vector x. And in this inequality, this matrix I is the Fisher information matrix. And if we assume that the data is normally distributed with a fixed standard deviation, it actually has a very simple and elegant form. So it looks like this. And basically all we have to do is calculate the partial derivatives of our model, of our diffusion model, with respect to the dependent variables of the model, put them in a vector, multiply that with the transpose, and we have the Fisher information matrix. Then we can take the inverse of it, and then we will get a covariance matrix with, on the diagonal elements, the variances of our parameters. And this makes the CRLB like a very efficient way of predicting the variance of your model parameters without having to resort to costly simulations. So let's apply this knowledge to the simplest possible diffusion experiment we can do, so an ADC measurement. So the idea is very simple. So we have a very minimal acquisition requirement. We just have a single image without diffusion weighting and then one image with diffusion weighting. And we do not consider multiple directions, so only the p-value dependence. So the model behind it is also very simple. So it's a simple exponential decay model. But despite its simplicity, it provides a very powerful contrast, for example, in stroke imaging. So let's apply what we have learned about the CRLB to this specific model. So the forward model F is now simply this exponential decay model. The dependent variables are the non-diffusion weighted signal S0 and the apparent diffusion coefficient D. So we just have to calculate the partial derivatives of this function with respect to S0 and D, put them in a vector, multiply that with the transpose. Then we have the Fisher information matrix, which is a small 2x2 matrix, invert it, and then on the diagonal of that we end up with the variances of S0 and the ADC. So if you want to do these calculations, I've prepared a GitHub repository on my GitHub account where you can look at these derivations and experiment with them. So we can already do quite powerful things with this. So the first thing that we can do is answer the question, what is the optimal B-value for ADC imaging? So I've plotted that here in this graph. So on the x-axis we have the B-value, and on the y-axis we have the corresponding relative SNR for ADC. And you can immediately see that the optimal B-value depends on the apparent diffusion coefficient of the tissue under investigation. So this means that if you move from brain imaging to imaging in another organ like muscles or heart, or if you move from in vivo to ex vivo diffusion MRI, you will probably have to adjust your B-value. So let's look at this relation between ADC and optimal B-value a little bit more. So now I've plotted on the x-axis the ADC, on the y-axis the optimal B-value, and then we see this clear relationship. And we can actually approximate it very accurately with this rule of thumb. So the optimal B-value is about 1 over the ADC of the underlying tissue, or 1.1 to be more precise. Another interesting question that we can look at is whether one non-diffusion weighted scan is enough. And so that's what I looked at here. So on the x-axis, I have the proportion of non-diffusion weighted scans in the experiment. And on the y-axis, the SNR gain relative to using just one scan. And you can see that the optimal number, or the optimal proportion, is surprisingly high. So it's 1/4 of the data that we should, in this case at least, dedicate to non-diffusion weighted images. So this number itself is not that important, but in general, it's important to keep in mind that if you design your sequence, you also add enough non-diffusion weighted images, because they will also affect the precision of your higher order parameters. Okay, so let's make it a little bit more interesting. So we had the simple ADC measurement, and now what we can do is add multiple directions and make it into a DTI sequence. So we will still keep the relatively low B values of ADC, and we will also use relatively low amounts of directions. So the model behind it is very similar to the ADC model, but now the diffusion coefficient has become a tensor, and we also have to take into account the gradient orientations. And what this allows us to do is to not only quantify the ADC, but also quantify the orientation dependence, or anisotropy, of diffusion. And this will enable us to estimate fiber orientations and do exciting things like fiber tracking. So how many directions do we need for DTI? So for the B value, we can sort of rely on the optimal B values from the ADC experiment. But for the number of directions, so minimally we need 6, because otherwise the system of equations is underdetermined, but more is of course always better for SNR. What's actually more important than the number is the distribution of the samples on the sphere. So here I've shown a lot of samples, but they're not very well distributed on the sphere. So the general recommendation is to use a tool like electrostatic repulsion to evenly distribute the gradients over the sphere. Then let's move to a Hardy acquisition. So Hardy stands for High Angular Resolution Diffusion Imaging. So compared to the DTI sequence, what we add is, first we increase the B value significantly, and then we also significantly increase the number of directions. And the main goal is, or what these sequences capitalize on, is angular resolution, with the main goal of resolving multiple fiber orientations. And because of this, it's really the staple acquisition that people go to for fiber tracking. So let's explore this Hardy signal in a bit more detail. So, so one thing that we immediately notice is that these images have quite low SNR. That's because of the strong diffusion weighting. But if we move through them, if we move through the different orientations, we do see that there's a very nice angular contrast in them. So to better visualize this, we can just pick out one voxel and then plot the signal intensity onto the sphere, where the radius is proportional to the diffusion MRI signal along that corresponding direction. So let's look at what this looks like in a real brain. So I'm actually trying to isolate a single fiber voxel here. So here's one. So the fiber orientation is here left to right. So along the fiber orientation, the diffusion is almost unhindered. So there's a lot of the signal is gone, and then perpendicular to it, there's a lot of restriction of the diffusion. So there, the diffusion weighted signal is almost preserved. So this is at a B value of 2,800. If we then move to lower and lower B values, we can see that the mean signal intensity increases, but more importantly, also these signal profiles will become a lot fatter. So you'll be losing angular resolution. And if we go back to higher B values, we again get these nice and sharp signal profiles. So this tells you that angular resolution in diffusion MRI is determined primarily by the B value and only secondarily by the number of directions in your experiment. So what are the optimal B value and for Hardy? What's the optimal B value for Hardy then, and how many directions should we acquire? So this is something that was answered very elegantly in this paper by Donald Tournier et al. So what they did was they started with a high-quality diffusion-weighted data set with 500 directions and B values ranging up to B5000. And then they analyzed the angular frequency content in single fiber voxels using spherical harmonic series. And this is what they found. So they found first that the SH terms above order 8 are negligible. And this suggests that a minimum of 45 directions is sufficient, at least to characterize the angular frequencies in the signal. Of course, in practice, you want more directions because that will also improve your precision. Another thing that they found was that SH terms above order 0 level off at B3000. And this suggests that a B value of 3000 already provides you the highest achievable angular resolution. So does this mean that we don't want to ever acquire B values above B3000? Of course not, because going beyond B3000 can still provide you very relevant information in the radial domain. So that's the domain of the B value dependency. So let's now move on to multi-shell. So if this is the Hardy acquisition, what multi-shell acquisitions change is they add measures at multiple B values. And because typically we only select B values from a discrete set, we end up with these nice concentric shell-wise acquisitions. So the models behind it are the typical DKI model, but also multi-compartment models and microstructural models. And what multi-shell acquisitions capitalize on is information about the radial domain or the B value dependency of the signal. So let's explore this radial dependency in a bit more detail. So here we have the average diffusion-weighted signal for increasing B values. You can see as the B value increases, we have more diffusion-induced signal loss. And what's interesting is that the rate at which this happens depends strongly on the tissue type or the underlying microstructure. And because each tissue type or each underlying microstructure has its own characteristic decay curve, we can use this to tease apart multiple compartments. So that's why multi-shell is really the go-to sequence for multi-compartment modeling. So what are the optimal B values and directions for multi-shell imaging then? So first, of course, this will depend on your specific multi-compartment model. So how can we then make general recommendations? So there's two approaches that I've come across in the literature. So the first one is to use a signal representation model. So that's a model that provides a statistical description of your signal without really decomposing the signal into multiple compartments. And then use the CRLB optimization to maximize the precision of its parameters. Or we can take a completely model agnostic route where we try to estimate the information content in the signal and then try to maximize that information content. So let's first look at the first approach. So for this, there is an interesting paper from Poth et al. From 2010. So they used diffusion kurtosis imaging model, which captures non-mono exponential decay, which you get if you have multiple underlying compartments, but it does so without explicitly decomposing the signal into multiple compartments. So you can think of it kind of as a generic model for multi-shell data, at least if your B values are not too high. And then they minimized the CRLB for mean kurtosis. And they found that they found a 4-shell acquisition scheme with B0, B700, B1200, and 2800 with increasing numbers of directions as the B value increased, which is not surprising, of course, because if you go to higher B values, there's multiple things going on. The SNR is lower, but also the angular frequencies increase, but also the information content or the relevant contrast is there. So it makes sense that if we move to higher B values, that we acquire more directions. And then there was also another approach that I could find, which was more model agnostic, more data driven. So what they did here was they acquired very densely sampled MRI data with multiple B values, lots of directions. Then they averaged within each shell, so only keeping the B value dependence. And then they performed a singular value decomposition, which offers the linear breakdown of the signal in terms of effects and relative contributions. And then they estimated the effect size for each coefficient of that basis and tried to identify the parameters that provide optimal sensitivity. And they did this study in neonates, but their optimal acquisition scheme was actually surprisingly similar to the ones that from the paper from Poth et al., which operated on adult mean kurtosis distributions. But the general trend is that, we need to acquire more directions at the higher B values, and we benefit from a lot from multiple B value shells. Okay, so let's now finally move to higher dimensional acquisitions. So these are acquisitions where we go beyond the traditional multi-shell setting and really extend the dimensionality of our measurement space. So if this is our traditional multi-shell scheme, we can no longer fit the higher dimensional scheme within this 2D plot. So, but you have to think of it like this. So we take, so we just add an additional dimension, for example, for the B-tensor shape, so whereby we acquire images which are sensitive not only for diffusion along a specific direction, like you have in the linear tensor encoding, but also within the specific plane with planar tensor encoding, or regardless of orientation, like in spherical tensor encoding. And now we can also add another dimension with echo time, for example, echo time dependence, for example, like Philip has already showed you in great length. And of course, it doesn't stop here. We can keep adding multiple dimensions. We can add time dependence, exchange dependence, etc. So what is the motivation for going to these higher dimensional acquisitions? So microstructure modeling, it holds great promise, because it can, in theory, it can provide us with microscopic information, but then in vivo. So it allows us to look into the tissue microstructure without having to cut open the patient. So if that worked, that would be fantastic. Unfortunately, there's been increasing evidence that multi-shell data is simply not rich enough in terms of information content to unambiguously distinguish between multiple microscopic substrates. So the problem is that you have multiple sets of microstructural parameters that will describe your data equally well. So you have an ill-posed problem. So typically this is addressed by using constraints that favor a particular solution. But the problem with this is that there's also increasing evidence that a lot of these constraints are not as widely applicable as previously thought. So the idea of higher dimension acquisitions is to add independent image contrast that can potentially reduce this ill-posed nature, and doing so without having to rely on constraints. And because these higher dimensional acquisitions become more complex because of all the dimensions, there's also probably optimal experimental design is becoming more relevant than ever. So let's look at some two examples of optimal experimental design for higher dimensional acquisitions. So one is one that I did myself together with Philip. So the idea was to extend multi-tissue spherical deconvolution to tensor-valued diffusion MRI. And when we did that, we wanted to figure out what the optimal B-tensor shapes were if we were doing this. So we started from a data set with multiple B-tensor shapes consisting of 183 samples in total. And from that, so which contained linear tensor encoding, planar tensor encoding, and spherical tensor encoding. And from that, we then selected the optimal subset of 61 samples that minimizes the variance of the apparent tissue densities in this model. And this way we could go to a sequence with just 61 images with a mixture of linear and spherical tensor encoding, which took the same amount of time as just the linear tensor encoding alone. And if we then looked at the root mean squared error of the apparent tissue densities, we could see that the optimized scheme had reduced the root mean square error by a factor of 2 compared to the conventional linear tensor encoding. So we gain in precision by a factor of 2 without adding meaningful scan time. And then another example that I came across that looked at this problem from the microstructural modeling angle. So they tried to reduce the ill-posed nature of a 2-compartment microstructure model with a stick for the intra-axonal diffusion and a zeppelin for the extra-axonal diffusion. And they looked at optimal B-tensor encoding, optimal echo times, all without constraints. So they optimized using the CRLB, B-value, B-tensor, anisotropy, echo time, and number of directions for a predetermined number of shells. And what they came up with was then 10 unique combinations of B-values, B-tensor shapes, and echo times. But yeah, the sequence itself is not that important to remember. But what is important to remember is the effect that optimizing the sequence had on the parameters. So, for example, in this plot, we see the effect of adding B-tensor shapes in the mix. So first, we had, if we only have linear tensor encoding, we had a lot of variance in the measurements. But if we then allowed multiple B-tensor shapes, we could reduce the variance by a factor of 10 almost. Also, increasing the range of echo times helped a lot, and also allowing much more shells than what we would traditionally do. So this is just an example to show you that as we go to higher and higher dimensional acquisitions, optimal experimental design becomes more and more important, and we can actually gain either a lot of time or gain a lot of information content by doing so. Okay, so to summarize, so I started with a simple ADC measurement on, which only involved a single diffusion-weighted image along a single direction and a single OB value. Then we went to DTI, which added the directional dependence. Then we went to Hardy, which added higher B values and much more directions. And yeah, together these three, well, they're still very relevant, but the thing with multi-shell imaging is that it kind of encapsulates all of them. So that's why multi-shell imaging has now become more or less like mainstream or the minimal requirement for diffusion-weighted imaging. And then finally, I've also showed you more cutting-edge techniques, which extend the sequences to a high-dimensional acquisition space. And what is important to realize is that just adding more complexity to your acquisition is not enough to have an advanced acquisition. We also have to make sure that we add the specific information that we need to support your specific model or your specific hypothesis. So each time we move to the right on this axis, we want to make sure we go up on the information content axis as much as possible. And that is what optimal experimental design can help us do. So this concludes my presentation. So if there are any questions, I'm happy to take them now or offline.